I'm a lecturer at Stanford University. I got my Ph.D. also at Stanford, and part of that work was looking at the geology's coastline. So I'm mostly a marine geologist, um, looking at sort of like submarine geology, like what's underneath the water. And so with that, there's lots of intersectionality with kayaking and coastal processes. I myself am not a kayaker whatsoever, so if I make any kayaking faux pas, please feel free to point and laugh. No harm, no foul there. I have kayaked Elkhorn Slough a couple times though. So does that make me a sea kayaker? I'm not sure. So yeah, the title of the talk is The Geology of Bay Area's Coastline, aka cool rocks you can now point at to next time when you go kayaking. So for example here, this is a view looking north from Muscle Rock, which would be just to our left here. And all of these rocks are a formation that make up what the city of San Francisco mostly sits on, which is called the Merced Formation. It's about a 2 million-year-old sandstone, and it actually records a series of inundations or flooding events where the bay was completely flooded, San Francisco was flooded, and then sea level dropped or regressed back down. We can actually see those records of sea level fall and rise due to changes in climate in the geologic recent past, like 2 million years ago. So let's just set the stage for folks in California geology. So California, you can think of, was sort of born, if you will, during a period of time called the Mesozoic. That's between approximately 300 and 65 million years ago. And during that time, the configuration of the western coast of North America and thus California looked a lot different. The Pacific plate was actually being shoved underneath North America. This is a process known as subduction, where a more dense tectonic plate is actually moving underneath a more buoyant tectonic plate. Usually it's an oceanic plate getting pushed underneath a continental plate. And that process actually causes a lot of deformation in mountain building. And where that contact is occurring, we get the creation of what's known as an accretionary wedge. That accretionary wedge is where there's a whole lot of stresses happening right at the trench, the deepest part of that ocean basin. So you get all sorts of folds and faults there. And then you also get, of course, the presence of volcanoes. And what's actually happening is that materials and sediments and minerals that make up the oceanic crust actually have little bits of water in them. And when you exert high amounts of pressure and high amounts of temperature, but mostly pressure really here, that water then gets released into the underlying mantle, and it actually lowers the melting point of the mantle. And that lowering of the melting point actually causes melting to form, and those melts then rise to the surface and form volcanoes. And so this is when the Sierra Nevada mountains, for example, were born. And so now looking at a cross section of this, this is an idealized cross section of what California would have looked like 100 million years ago in the Cretaceous period when dinosaurs were roaming the earth. The Farallon plate, which no longer exists on the surface anymore, was an oceanic plate being pushed underneath California, and it formed three main, what I'll call tectonic provinces that now is sort of the underlying footprint of California. Well, there's the Sierra Nevadas, which is beautiful, but maybe not of interest to well, I'm sure it's of interest, but not a lot of seaways to kayak in the Sierra Nevada. So we won't be focusing too much on that. And then there's this accretionary wedge, and that's what we'll be focusing on mostly, which is that contact between this underlying oceanic plate and this overlying North American plate, where a lot of stresses are occurring. Because all those stresses are occurring, you're getting all of these faults. That's what these arrows are supposed to represent. And you're getting a bunch of folded rocks as well, tectonic processes, deformation. And in between those two, there's this thing called a basin, in a low point between these two high points where sediment accumulates. And that is the Great Valley. And so when you look at California, and you look at a geologic map of California where in red is the Sierra Nevada, in yellow is the Great Valley, and this sort of melange of different colors of this light green and orange is the accretionary prism. It's actually very similar to what, for example, Sumatra or northeastern Indonesia looks like currently today, where the Indian Ocean plate is actually being pushed underneath the Eurasian plate, And it's forming a subduction zone here, two plates pushing underneath each other, making a volcanic arc. And it's forming a volcanic arc in red, a basin known as a forearc basin in yellow, and an accretionary prism in green. And so when we look at a geologic map of California, we're seeing sort of the footprint of when California was born, these three main tectonic provinces. This is just a simplified version of this exact of this uh, the California geology in general, where in red we've got the Sierra Nevadas, in yellow we have the Great Valley, and in blues and greens and pinks we have the accretionary wedge, which is sometimes referred to as the Franciscan complex or the Franciscan assemblage, which is the name of the rocks that make up sort of the margin of California. And so after that big subduction event throughout the Mesozoic, where we sort of built California and built the basic footprint, a complexity happened. And that complexity is a well-known feature that every person knows. Everyone knows the name of at least one fault, and that's, of course, the San Andreas Fault. It's famous because there are a lot of earthquakes on it. It's in California. It's a well-known place. How did that actually form? Well, at the last gasp of the Farallon Plate, so this is the contact between the Farallon Plate and the Pacific Plate, it's going to get pushed underneath North America here. And when it gets pushed underneath North America, it's actually going to come in contact with the Pacific Plate. And note that the tectonic directions, the plate tectonic directions, are actually divergent from each other. And that divergence is actually going to change the configuration of that tectonic boundary and start to actually pull open California. And you see how the states are all squished right now because they were about 10 million years ago. And now they're being opened up as the San Andreas Fault is moving from side to side from each other and actually pulling apart bits of California. And so all of this orange area is what we call thinned or attenuated crust that has been stretched open due to stresses from the San Andreas Fault, which again is a transform boundary where two plates are moving side by side as opposed to converging towards each other. And so when we look at a fault map now, we can see this is the main San Andreas Fault, kind of defines the spine of California. And everything now on the left of this big pink line here, that's mostly the San Andreas Fault, is actually a part of the Pacific Plate. It's a part of California that's been captured by the Pacific Plate on the San Andreas Fault. And everything here is now moving to the northwest. So I'm currently pretty much on the San Andreas Fault. And if I drove about 10 minutes to my west here, I'm on the Santa Cruz Mountains. Then if I sat there for another million years, I would move a few meters, few hundred meters to the northwest. So everything here west of the San Andreas Fault is eventually going to make its way to Alaska. And of course, this red zone is where big earthquakes occur as well. We are living on the plate tectonic edge. And where there is an edge between two plate tectonics, there are a lot of earthquakes. And in the more recent past, about 18,000 years ago, which is geologically very recent, the Bay Area actually looked a lot different. The coastline was actually about 22 kilometers outboard of what it currently is. The continental shelf now is completely inundated. We don't see that. So at about 18,000 years ago, though, sea level began to rise again as the glaciers from the last ice age began to melt. And now it's starting to inundate the Bay Area here, inundating parts of San Joaquin and Sacramento rivers. And then it regresses again into its current configuration. And you can see that the Farallon Islands here are now a series of islands, but back 18,000 years ago or so, they were actually on land. And those are just the last little gasps of the continent that are still subaerially exposed. So a lot has happened in the Bay Area in both a long-term geologic period of time between like 300 million years ago and now, and also dynamics on the tens of thousands of year scale. And so the hope with this talk is to give you a geology field trip from the perspective of a sea kayaker within the Bay Area. So we're going to start up at Tomales Bay near Point Reyes, and we're going to make our way down as if you could kayak all the way down the coastline to see some cool features that sort of show little remnants, little bits of interesting features that tell the story of the geology of California. So the first place to go that I thought of, which was immediate, and I even saw on your website, someone did a basic write-up on some of these features. So I not even original in this, but Tomales Bay, really fascinating geographic location, right? The sort of morphology of it is very strange. It's this inundated bay that's incredibly linear. And some of you probably already know this, but it's really linear because the San Andreas Fault, the one fault that we all know the name of, actually runs right through it. Where two plate boundaries are rubbing against each other, that's actually going to cause a lot of erosion. And where there's a lot of erosion, you're typically going to carve out river valleys. And because we're in a sea level high right now, that river valley, Tomales Bay, has been inundated and flooded and now is salty water or brackish water. And there's also tidal channels as well. And so, from this perspective, where we're looking, we're on the North American plate, and on the other side of Tomales Bay, Point Reyes is actually the Pacific plate. So if we were to sit here, we could watch Point Reyes move towards Alaska if we could sit there for 10 million years or so. Pretty cool. And so you guys could actually go out and kayak here, and when you're kayaking there, you are kayaking on a plate boundary between North America and the Pacific plate. And you can tell your friends, like, did you know we're on a plate boundary? And did you know that where there are plate boundaries, there are a whole lot of earthquakes? So here is the San Andreas Fault in black here. It continues on through Tomales Bay on this geologic map. And the San Andreas Fault is responsible for a series of very large earthquakes that have happened in the Bay Area. One in the further in the past is the 1906 earthquake, which effectively leveled San Francisco and parts of the Bay Area. This is, for example, a view of Sutter Street in San Francisco, and they were all brick and mortar buildings, which are very unstable in earthquakes. So all of them effectively collapsed. And then there was also a huge fire because gas lines broke as well. And so then San Francisco was on fire, 3,000 people died, millions of dollars of damages. And then in the more recent past, oh, and this shout out to Stanford. If you didn't know, if you've been to Stanford's campus, you might not recognize this big arch. This big arch actually was built when the main quad of Stanford University was built, but during the 1906 earthquake, it was partially destroyed, and the designers decided that it actually looks better without it. So this big arch does not exist anymore after the 1906 earthquake. In the more recent past, Loma Prieta. So this was another earthquake that happened on the San Andreas Fault, magnitude 6.9, killed 63 people, mostly people on highways because these double-deck highways in the East Bay tend to collapse and pancake on each other. So big faults are occurring on the San Andreas Fault, but I still recommend going to Tomales Bay because I think honestly being in the bay while an earthquake is happening is probably a pretty safe place to be. You would prefer to be, I would say, sea kayaking rather than on a double-decker highway, for example. So don't let it discourage you. Go to Tomales Bay. So if we go further south from Tomales Bay, now into the main inlet between San Francisco Bay and the Pacific Ocean, we can head actually into the Marin Headlands and also Angel Island. And we can start to see evidence for that ancient subduction zone. So where there's that ancient subduction zone, remember there's this accretionary wedge or Franciscan assemblage where all of this oceanic material is scraping up against the continent. And so when we look closely at the rocks there, we can actually see evidence for this old oceanic crust that's been scraped against that. And that's most brilliantly exposed at the Point Bonita lighthouse in the Marin Headlands. If you've never been there, it's worth a trip. You can go kayaking around there as far as I'm aware, and you can also walk out there. And if you look at Point Bonita Lighthouse, it's on this weird black rock. This weird black rock is a volcanic rock called basalt. And basalt most often forms in ocean basins where two plates are moving away from each other, and it produces a very specific type of rock called basalt, which is made up of heavy elements like magnesium and iron. And they form these really cool things called pillows. And I'll show you why they're called pillows in a second. You can actually see these old pillow basalts that make up old oceanic crust uh, that is Mesozoic in age, hundreds of millions of years old, that we now built a lighthouse on top of. And if you go further inboard towards Angel Island or towards Tiburon, you can actually see a bunch of metamorphic rocks. And those metamorphic rocks are called green schists, they're blue schists, and also this really cool rock called serpentinite. All of these rocks represent really high pressure conditions that metamorphosed or changed the mineralogy of those original rocks into a new rock. And you can see them now in that make up all of Angel Island, for example, is this Franciscan assemblage. So if you go kayaking around here, you're kayaking around this old, this ancient oceanic crust that has now been completely subducted away. This is the last gasp evidence of it. This is just what that looks like. It might be a little loud on the video, so apology for that. How pillow basalts are made. So this is a subaqueous volcanic eruption of basalt, and it's cooling instantaneously once it reaches the surface. So as it cools, it sort of inflates and freezes in place. And the most efficient way to do that is to expand outward in all directions, which makes a sphere. And so we call them pillows because they kind of look like pillows, like you would want to rest your head on it. But I wouldn't recommend it because that thing is about 1100 degrees Celsius. So that's how pillow basalts are made in the modern. And we now built a lighthouse on those pillow basalts. Pretty cool. This is just a figure to try to show that as well, those pillow basalts. This is kind of what they look like, where they sort of ooze out from one another as they find cracks and seeps throughout that sort of basaltic flow. Very similar rocks to what you'd expect in a place like Hawaii, for example. You see these sorts of rocks in ocean islands like Hawaii. Also in the Marin Headlands, you might notice that there's a lot of these really weathered, oxidized, um, red rocks that have, if you look closely, they have these like, this is actually bedding. So these are actually layers of rock. And usually layers of rock are deposited flat. But these rocks, if you look, the layers are subvertical and they're all folded about. Well, that's because, again, we're within this Franciscan assemblage or accretionary wedge where we pushed and squeezed everything together. We've actually folded all of these rocks up. This is a rock, a sedimentary rock called a chert. And these cherts only form in deep ocean basins for the most part, where these tiny critters on the millimeter and submillimeter scale called radiolaria precipitate these beautifully intricate and alien-like shells made up of silica and oxygen, SiO2 or quartz. And then eventually those critters that have some carbon in them, they die, the carbon weathers away, but their exoskeletons stay behind. And if you do that for long enough, you're going to be left with a layer of these critters. You bury those critters, and they actually turn into a rock that's made up mostly of SiO2 or quartz. That's what chert is. And so if you're in the Marin Headlands, if you're just driving or hiking, or as you go around Point Bonito Lighthouse, as you're kayaking, you're going to notice a shift to these bright red rocks. Those bright red rocks are these radiolarian cherts from this ancient ocean basin that's now no more. If you also head to Rodeo Beach, which is nearby in the Marin Headlands, you might notice this sort of variegated green and orange and red sands that actually make up Rodeo Beach. And those are actually weathered bits of this chert exactly. And so Rodeo Beach is really cool, and geologists love to go there because it's sort of a red sand beach, sort of rare. And it's deriving directly from these cherts that are weathering out from the local bedrock in that area. Moving further south, I know that you guys probably care a lot about tides, and you guys know that the tides actually at the inlet outlet of the bay can actually be very severe. And the reason for that is that there's quite a tight constriction there. And so when the tides ebb and flow out of that system, the velocity has to increase as it gets constricted. And if the velocity actually increases, you're actually able to move a lot of sediment on the seafloor. So this is a digital elevation model or a map of the submarine elevation, what we call the bathymetry of the bay. And we can actually see these huge dune systems. These dune systems are forming because the currents are so strong in the bay that, just to give you for scale here, this little tiny guy, that's the Statue of Liberty, which is approximately 32 meters high. One of these dunes is taller than the Statue of Liberty from the beginning of its copper bottom of her dress to the top of the her little flame. So that's about one Statue of Liberty. These are huge, massive dunes. They would be like Saharan style dunes if we were to drain the bay. And this is all due to the constriction and the strong tidal currents that are ebbing and flowing out from the bay into the Pacific Ocean. So it's just another view of it. And I just thought it would be of interest to you all because I know kayaking is really popular around here and that the currents are probably likely something to consider and might be dangerous. And the reason for that is that tight constriction. And we can see the geologic evidence of that too, between the bay and the Pacific Ocean, these huge tides, this really incised portion of the bay, really deep. Very cool. Let's move further south to Devil's Slide. Found this. Can you guys see this Instagram? Yeah. Yeah, so I don't know if this person's in Basque or not, but this person actually kayaked around Point San Pedro. Um, and you can see they're kayaking around rocks and all of that. Um, and they're actually kayaking right next to Devil's Slide. I know there's some restrictions about where you can kayak at Devil's Slide, but apparently you can go around here, or at least you have been able to. And look at all these beautiful rocks. What are all these beautiful rocks in Devil's Slide? Let's talk about that. Back to this. You guys see my PowerPoint? Yeah? Okay. So this is an aerial view of Devil's Slide here. This is actually an abandoned portion of Highway 1. Um, and you can see why it was abandoned, right? A lot of uplift has occurred here, right along the bay. And where there's a lot of uplift, there's mountains, and the relief is high, and therefore the actual material, the land, is very unstable, meaning that there's a whole lot of landslides. So all of this exposed bedrock here is exposed here because there's big landslides that are occurring frequently. And it was actually so expensive and so dangerous to keep this part of Highway 1 open that they instead decided to drill a huge tunnel, the second longest tunnel in California, underneath Monterey Mountain, which is right here, which is also made out of granite, which is really hard. So it costs billions of dollars, is incredibly intensive, and it was all because you could not keep this part of the bay safely open. These are just some images of that, where these are old landslide scarps. So these are old landslides and mapped out zones of areas that have recently slid. And these are also areas on the right here where we've tried our best to build roads or railroads through here. You can actually see evidence for the old railroad that used to go here. There was actually, you can see the grade actually. They tried to put a railroad through here, and it was a massive failure. And just like Highway 1, also a massive failure. So they ended up actually constructing the Tom Lantos tunnels here in order to just mitigate Highway 1. So here we are heading down to Devil's Slide. And Devil's Slide, one thing that's really cool about it is now that it's a walkway, you can walk or you could kayak around and check out Point San Pedro. And if you looked at Point San Pedro, you'd see all of these really finely bedded, these like very pretty layered rocks of sand and mud and sand and mud. Those little layers of sand and mud are actually the ancient remnants of what we call a submarine canyon and submarine channel. You can think of it as just a canyon that is itself underwater. They're the main conduits by which sediment makes its way from the continent into the ocean basin. Vast amounts of sediment are funneled through here, and therefore there are vast deposits as well. And so this is me talking very excitedly to some students, and you can see how excited they are. Look how excited they are. About these rocks that are now exposed at Devil's Slide, that record this ancient submarine canyon. As we go further south, we're going to start to see that a lot of the rocks on the coast are actually these records of these old submarine canyons that have now been uplifted due to the stresses on the San Andreas Fault and now are exposed for scientists and geologists to study. This is just a really cool video. Beneath the beautiful blue waters of Monterey, it lies a geological. Well, I'm going to talk over it instead. So this is a satellite view. We're going to drain the bay, the Monterey Bay, and we're actually going to expose the largest submarine canyon on the coast of California called Monterey Canyon. And if you were to drain the bay, it would be as if you were looking out at a vista comparable to the Grand Canyon, and you just can't see it because it's underwater. Um, Also, fun fact, these canyons were not really discovered until post-World War II when we actually started using sonar and radar technologies to actually image the seafloor at high resolution. These models here are at super high resolution because the Monterey Bay Aquarium Research Institute um, imaged this in great detail. And so we see these underwater today, and we also see the vestiges of these ancient canyons uh, glommed on to the continent now. So they were originally deposited at like 4 kilometers water depth, and now they're at sea level, or they make up the mountains that we or the cities that we live on or live in. All right, let's go further south. Moving down to Half Moon Bay, sort of an excursion away from kayaking, but perhaps a potential hazard to be aware of, which I'm sure you all are, which is mavericks. So if you head down to Half Moon Bay, as here's our little kayaking friend, we're heading down to Half Moon Bay. Here's the Half Moon Bay Airport. Seems like a perfectly safe, lovely airport. Well, turns out there's a fault right there, and it's a relatively active fault called the San Gregorio Fault. It's related to the San Andreas Fault, so it's moving in the same direction, but it's a totally different fault system. And it has been predicted to create a magnitude 7.0 or 6 point something earthquake, which is comparable to the 1989 Loma Prieta earthquake. So big earthquakes are happening here. One of the features or related things by the fact that there is a fault right here, here's the Half Moon Bay Airport, of course, is that you actually get a lot of deformation. And that deformation is actually deforming and distorting the rocks in the ocean. So all of these sort of kind of arcuate structures here, those are actually rocks on the seafloor that have been folded and squeezed together. And because they've been folded and squeezed together in a certain way, it actually has caused a convergence of wave energy exactly at Mavericks Beach or Pillar Point, right at Half Moon Bay, such that it produces dramatic music. During big storm surges, it can produce really dramatic waves. And so this is a cool intersection between like how tides and waves are actually controlled by the underlying geology. The reason Mavericks has such big waves like this is because it's actually the underlying geology, which is causing those waves to converge at a single point and produce really spectacular waves. All right. Moving further south towards the less populated parts of the coastline where we're not allowed to build new structures. So thankfully, all these beaches have been beautifully preserved. This is my favorite local state beach, San Gregorio State Beach. I highly recommend going if you've never gone. It's absolutely gorgeous, and it houses some really cool geology, some evidence of past eruptions. So this is San Gregorio Beach. We're going to head down a little bit further south of Half Moon Bay, a 20-minute drive or so. And this is the San Gregorio Creek here. It's an important creek for coho salmon to swim upstream, have their babies, and was a critical resource for Ohlone people, indigenous people. Their food resource was actually a main portion was from San Gregorio Creek here. So here are some rocks exposed to San Gregorio Creek. And remember how I said that sedimentary rocks, they tend to form nice flat layers. But if you look closely, you can see like, whoa, there's like some crazy like contorted layers here. Those contortions are a feature we call soft sed deformation. But what actually happened is that this is a big ash bed from a volcanic eruption, and it was really hot. And because it was hot and it deposited really quickly onto these underlying rocks, it actually caused foundering. Imagine like sticking your boot or into like a swampy, muddy area and how that would deform the underlying mud. Same concept here, but imagine an incandescent hot ash covering this area. We can actually look at the minerals making up the ash bed and from that derive an age by looking at radioactive elements within those minerals. And we can look at the geochemistry to actually argue that this ash bed is deriving all the way from an eruption from Mount Lassen. So here's just the current configuration of Mount Lassen. It's actually a little bit older than the modern configuration of Mount Lassen, which is only about 800,000 years old, whereas these rocks are about 2 million years old. And another fun fact I love to take my students here is when you look at the Parissima Formation, which is the underlying sedimentary rocks and the above sedimentary rocks, you get these amazing shells. These are filled with life. There's little burrows and worms and snails. They're great doorstops, so I recommend going to a beach that has the Parissima because they can like make great little doorstops or good rock art or good for any sort of landscaping need. And so it's full of life. And then, of course, the ash bed, there's no life there. But then guess what? Above the ash bed, did all of the life go extinct? No. Life is resilient and all of the shells return. So it's a nice story to kind of show the resilience of life on Earth and how we bounce back from traumatic events. As we move further south into some of the smaller beaches, like towards Pigeon Point Lighthouse, for example, or this beach, which is called Pebble Beach at Bean Hollow, we see more and more evidence for all of these ancient underwater submarine flows called turbidity currents. And turbidity currents you can think of are like um, these avalanches of material, but instead of snow, they're water that is laden with sediment. And because water that's mixed with sediment is slightly denser than the overlying water that's not rich in sediment, it will actually flow downhill, like in this flume experiment, due to the forces of gravity. These things are actually incredibly erosive. They can move at almost 100 miles per hour. And we have actually been able to track their flow by how they break steel telecommunication cables on the seabed. So we were actually able to, for example, in 1929, there was a big turbidity current, and it severed all of the communication cables from northwestern Canada to Britain. And we could actually calculate when it was there and therefore its velocity to figure out the flow of these things. These things are incredibly, incredibly strong and really fascinating events, thought to be perhaps related to earthquakes or large storms that destabilize the continental slope and then flow downhill due to the force of gravity. And when we look at the rocks actually that make up these beaches, well, these are actually all ancient sedimentary deposits of turbidity currents. So every single one of these layers that you see here from, in this case, Pebble Beach, represents one of these potentially catastrophic events that are happening offshore, these big turbidity currents. And this is one of the things that I study, for example, because I mean, who wouldn't? They're super cool, super interesting. As we move further south, you could head down towards Davenport and you could kayak around or near Sharkfin Cove, one of the most aesthetic beaches just north of Santa Cruz. And we see more evidence for these deep sea sediments. In this case, they're not turbidites, they're more of these cherts, but they're much younger. They're tens of millions of years old as opposed to 100 million years old. And these cherts are actually deposits of, again, these little critters that were living on the seafloor, died, and then deposited a layer of sediment. But how did these deep sea sediments get here? Like why are they were deposited at like 4 kilometers water depth and now they had to be uplifted onto the coastline? Well, if we look at a satellite map of the San Andreas Fault, we can see that it's not actually a perfectly straight line, but there's actually this little bend here. This little bend, what happens when you put a bend in a transform boundary, a boundary that's moving side by side? Well, this plate is wanting to move to the right. This plate, or to the southeast. This plate is wanting to move to the northwest. So when it's perfectly straight, they'll just move side by side. But in this case, because there's a bend, they're going to compress. And that compression makes mountains and will uplift parts of ocean basins adjacent to the continent, like here's Monterey Canyon, and will then expose them onto the surface. And so the Santa Cruz Mountains, the reason they're there is because of this bend in the San Andreas Fault. There are all these abandoned parts of the San Andreas Fault here as well that are no longer active, that have all these bends in them that we think are responsible for building the the Santa Cruz Mountains. The Santa Cruz Mountains, also fun fact, are only 3 million years old, which sounds really old, but remember the Earth is 4.567 billion years old, so not a lot of time actually. And so if you were to look at the coast 3 million years ago, if you were to sit in Palo Alto, like where I'm at, you wouldn't see any of these mountains. You would see a flat coastal plain. So thankfully, we have the San Andreas Fault to make this amazing topography to go check out when you're kayaking down the coastline. Um, But here's another weird fact, though. Look how flat it is right here. That's kind of weird. We expect like, oh, it's mountainous terrain. It should be rugged, right? Well, why is that? It's kind of interesting. So as the San Andreas Fault was squeezing and uplifting those mountains, what was also getting uplifted were the beaches themselves. And beaches are really flat places, right? Not a lot of topography on a beach. It's usually nice and flat. And so what actually happens is that you produce terraces of ancient beaches that are slowly have been uplifted over time. And scientists can actually map out these terraces and from that actually derive an uplift rate of the Santa Cruz Mountains. So if you actually look at a topographic profile of the mountains, they actually have, instead of like a just a nice, straight line, they kind of have or a sloped line, they kind of have a stair step pattern. Those stair-step patterns are actually ancient shorelines that have been uplifted slowly over time. We've named them the Santa Cruz Terrace, for example. Um, and funny enough, it's one of the reasons why this part of the coast is really great at for agriculture, for all your brassicas, your Brussels sprouts, and kales, because there's these nice flat areas that expose these nice soils that are getting a lot of nutrients from these ancient beach deposits. So it's why you get like really nice agricultural land right next to these big mountains. Um, cool intersection between geology and agriculture. Moving further south, as you kayak through Monterey Bay, you might notice that around here, wave action can actually be pretty high. Because so you can actually get some pretty nasty swell there. But as you move further south, you might actually notice a pretty dramatic shift in how waves, how high the amplitude of the waves are. And the reason being, I sort of gave it away, is that as you move further south here, you're actually moving from a shelf that is like 30-meter water depth, 100-meter water depth, to a canyon that is at that point a kilometer deep. And if you go from a shallow place where the waves could be really high there, but actually, if you're right above the Monterey Canyon, it can actually be quite a quiescent place where there's not a lot of wave action because waves really break best in shallow water. Whereas if you're in deep water, the energy of that wave can be compensated for by having a much thicker water column. And so you can actually get changes in wave action based on the underlying bathymetry that we can't even see. So next time you're planning a kayaking trip, like think about all of these cool intersections between what's like actually on the seafloor and what's controlling like, whether or not you're really seasick or you're in really calm waters. And then, of course, at the mouth of Monterey Canyon, so this is Monterey Canyon here, is probably one of the most famous places for people to go kayaking, which is, of course, Elkhorn Slough, an estuary, a tidal estuary, so it's like a flooded river valley, because we live in right now, a period of high sea level. And so this river valley has been flooded, and so there's brackish water, a mixture of fresh and salt water in this slough, second largest estuary in California, and of course, plenty of furry friends to go check out. Again, the only place that I've actually gone sea kayaking or kayaking. I don't know if this constitutes a sea kayaking or not. To check out the otters, which I loved, and I've done it a couple times because it was so great. Super calm water, very beautiful. And it's right at the mouth of this giant submarine canyon too. So it's cool to think about the connection from on land, Elkhorn Slough here, and a giant canyon system right at the mouth of Elkhorn Slough. And finally, if you head down to Point Lobos, I'll play this video and mute it. Um, you actually end up at the guts of a submarine canyon. So this is a formation called the Carmelo Formation that makes up Point Lobos State Reserve. And it makes all these like really coarse-grained sedimentary rocks. It's made up of all these coarse-grained sedimentary rocks. They're absolutely gorgeous. And they're actually the guts or like the ancient remnants of like that big submarine canyon like Monterey Canyon that have now been exposed on the sea surface. This is Steve Graham, professor at Stanford, talking about this. These gorgeous rocks, I recommend going if you can. A little harder to go to these days, but if you look out here, the Carmelo Formation is right here, and these big canyons are right there. And it kind of makes sense. Like you've caused a lot of deformation on the margin of this continent, and now you're exposing these ancient submarine canyons, and those processes are still happening today. Um, and we can see them both in bathymetry and we can see them in the rock record. So I think I'll leave it at that. Happy to take some questions. And thanks for your time and thanks for listening.
All right. Thank you, Dr. Dobbs. That was excellent. And I think, in my opinion, sea kayaking would definitely include Elkhorn Slough. So you're
Nice.
you're in good company.
Great.
Um, we'd start off. We got a bunch of questions in the chat, I think. Chris Lewis asked, "Do we know how often the turbidity currents occur?"
Mm. Yeah, that's an awesome question. So we thought for the longest time that during a sea level high stand or high sea levels, let me go back to this. Um, so notice how like besides Monterey Canyon, most canyons are actually not incising or cutting up straight to the continent. And so we thought for the longest time that during these high sea level periods of time, that these submarine canyons were just shut off because they weren't receiving sediment, so they couldn't flow. But then the Monterey Bay Aquarium Research Institute, which is right here, uh, who studies these canyons extensively, they put instrumentation down here and they've demonstrated that these flows happen very frequently. They happen you can get several of them within a year, for example. And they can be very erosive and they can actually modify the bottom of this canyon and erode the bottom part of this canyon. So we think that they happen pretty often on human timescales. Like you can get at least like I don't to put an exact number, I would say like expect between 0 and maybe 10 turbidity currents a year in a very active canyon to a very inactive canyon.
Yeah, related question in the chat from Brett Ann. Has the water from the big California Central Valley always gone out via the Golden Gate, and why is Monterey such a giant canyon underwater? I think you kind of touched on that one.
That's a good question. Off the top of my head, I believe that the major outlet for the Great Valley is um, the confluence between the San Joaquin and Sacramento rivers, and therefore goes out through the bay. Um, but it's a little more complicated than that because um, all of the sort of western side of the San Andreas Fault has been slowly moving northwest over time. And that has actually reconfigured the way California looks. The Great Valley probably had a lot of access to the open ocean, a lot more access than what is currently. So there are probably other uh, uh, exit points throughout the history of the Great Valley. And why is Monterey such a giant canyon underwater? The reason being is these turbidity currents. These turbidity currents are actually able, which are these sediment-laden flows that are happening underwater. They're actually able to erode vast amounts of sediment, and you can imagine them moving through this canyon and carving out these canyons. That's how we think these actually form. But It's a fun fact that like this science is still relatively new because the fidelity at which we image the seafloor is uh, the thing that we always say or had said about 10 years ago was like we have better imaging of Mars and the moon than we do of our own oceans. And that fact actually still holds true for most of our oceans. The like pixel size we have for like the ocean basins is on order of 1 kilometer by 1 kilometer. That's an individual pixel. So we're getting more and more data nowadays, though. So we're starting to get these beautiful images of these canyons.
All right, I got a couple hands up. Margot.
This is probably, oh, thank you a lot for this talk. This has been great.
Thank you.
And this is probably a little morphological detail that may be too detaily, but the second deepest place on the bay is between the Brothers Islands and the mainland. Why on
Mhm.
earth?
I'd have to look. Let's run over to Google Maps. Um, let's look at that. I I am not 100%. So that is,
It's up north of there.
oh, there's no bathymetry here.
Yeah, up right next to Point San Pablo there. You see those two little islands offshore from Point San Pablo?
Yes.
Yeah.
Yep.
So right between those two, between the East Brother and the point, is the second deepest part of the bay.
Yeah,
It's bizarre.
so you see how there's a constriction here? That
Yeah.
constriction is actually probably causing the ancient river that used to exist in the bay before it was flooded
Yeah.
to actually cut down. Uh,
Yeah. And there is a channel, but the main channel is where you would expect it to be.
I'd have to look at the bathymetry of the bay, but I think it's probably related to not a submarine channel, but an ancient river channel that's been inundated.
Mm.
Um, but my guess is that the constriction plus sometimes rivers they meander back and forth, and certain portions of the channel actually get abandoned and in favor of other portions of a channel. And so it could actually be a meander, what we call a meander cutoff, where that channel, the main channel got abandoned, and then that secondary channel got cut down into. But it's a great question. I don't know exactly why, so I'm mostly guessing there.
Thank you.
Kathleen.
It's actually Jan, yeah, on Kathleen's computer. Great talk. Thank you. Thank you very much. Question. South of Año Nuevo State Park, there's a beach where you find rocks that look like mollusk shells
Yeah,
embedded in gray, almost like clay that fossilized or hardened.
like
Can you,
this.
like exactly that? Can you explain how this comes into being?
Yes, so this is the Parissima Formation. It makes up most of the coastline south of, I'd say, Pacifica. Um, between Pacifica and Santa Cruz, most of the coast is Parissima. And
Oh,
Parissima Formation is mostly a sandstone. And you can imagine the depositional environment of this was actually an old beach. And so those old beaches housed a bunch of critters like that made shells. Um, and so you can imagine when you walk on a beach, sometimes you find an area that is really rich in shell material, like just like a little hump or hummock of like material. That's
mhm,
exactly what this was. This was like some bump on a beach that was rich in shells because currents kind of concentrated those coarser grained materials. And
uh-huh,
then when you bury it, all of these things are made out of calcium carbonate cement, like limestone. And if you bury it, actually, all that calcium carbonate in the shells actually produces a really strong cement that binds it together. And that ends up, then they weather out from the bedrock. And then you end up with these beautiful cobbles and clasts
mhm.
of these really shelly bits of parissima. So we love these as Bay Area geologists. You'll see them everywhere. in a geologist's home. That's why I had one.
Okay, yeah, I have a couple too. And what's interesting is if you have a bivalve, a mussel
Mhm.
cut crosswise, it looks romantically like a heart.
Yeah, it totally does. It totally does. They're beautiful. I have a few
Okay,
of them.
thank you.
Yeah, great question. Good observation.
Okay, we have Etan, which I believe we all owe Etan a big thank you for reaching out to you originally for this talk. Etan asks, what is the relationship between the submarine canyons and the Carmelo Formation at Point Lobos?
Yeah, great question. So the Carmelo Formation are actually thick turbidite deposits that, and they're really coarse grained. So they're sedimentary rocks. Like a sandstone is a sedimentary rock made out of sand, right? You can also get sedimentary rocks that are made out of gravel, bigger pieces of material. Those actually were deposits made by turbidity currents that are occurring in the center of a big submarine canyon, where when you're in the center of a big submarine canyon, that's going to be the highest energy flow. So you can move like boulders, you can move big cobbles and clasts, and then that will get buried, and you'll be left with the Carmelo Formation, which will be all of these bits of gravel effectively that were moving down through this canyon. So what's really odd is like when you think of a sedimentary rock and you think of like an ocean basin, you think like really quiet mud, like the chert we talked about. But it turns out that like in a canyon, you can get at like kilometers water depth, gravels moving at like 60 miles per hour on the seafloor. Crazy to think about.
All right, lots of questions here. We got one from Lisa, who has moved from the Bay Area to Vancouver Island, where I'm actually originally from. So she asks, do you have any info to correlate between NorCal coast and the Vancouver Island coast? I think it's a different plate system, but yeah.
Yeah, Vancouver Island, yes, you're correct. Everything north of Mendocino is actually still exposes the last gasp of the Farallon plate. So there's actually still subduction occurring there, where this plate that we now call the Juan de Fuca plate is being pushed underneath California and the Pacific Northwest, and that's producing the Cascades. And so when you look at a geologic map, for example, share my screen again. A geologic map of California. So look, going through this video here, we can see this is what I don't have Vancouver Island here, but um, this is the current configuration of California San Andreas Fault, and then there's this little bit of a plate here, and this plate is actually getting pushed underneath North America, and it's producing cascades, which are volcanoes. So those are subduction zone style volcanoes um, that are the last remnant of the subduction zone that used to be across the entire margin of Western North America back in the Mesozoic. Pretty cool.
Definitely. I don't know if you want to read Dorte's question. It's about the uplift of marine terraces.
Sure, Dorte. The uplift of marine terraces has always been a little difficult for me to understand. What uplifts them? It sounds like you attribute this all to motion along the San Andreas Fault. Is this true for all marine terraces along the California coast? Are these terraces big chunks of terrain that won't break apart and create new mountain ranges, are rather lifted as preserving horizontal layering? Yeah, so it is confusing because you think like, okay, uplift should actually be like continuous, and why would there be like these flat, like kind of stair step patterns? It's actually a quite a contentious point in geology, and my colleagues actually just published a paper on this about how deformation actually happens from earthquake events. And their hypothesis is that simply is that you don't actually have like continuous uplift over time, but actually you get these sporadic sort of bursts. And so what happens is that that terrace was actually sea level for which was stable over some geologic period of time. And then there was a period of relatively rapid, thousands, hundreds of thousands of years uplift that pushed it up, which then caused a new sea level to form, which then produced what we call a wave cut platform. So that then beveled out that area and made it flat again. And so the idea is that these terraces form in these sort of burps of uplift as opposed to a continuous motion. Now, by burp, I mean geologic burps. So like thousands of years, tens of thousands of years, maybe hundreds of thousands of years. Um, it's a great question, and I believe Dorothy was the geophysicist, so she could speak more about earthquakes than I can, I am sure.
Okay, Larry asks, what do you expect the water in Tomales Bay to do if there's an 8.0 on the Richter scale earthquake on
I
this?
expect it to shake a lot, but um, the thing about a liquid is that you can shear it all you want. It'll move back and forth all you want, no problem. Um, I would much rather be in Tomales Bay and getting a little shook up than being like in a building that I'm not sure is up to earthquake code. Um, so uh, yeah, I don't know exactly what would happen, but you probably wouldn't get a tsunami if you were worried about that. Um, I don't know if you guys got that tsunami warning. Those of you who live in the Bay Area, like about a year ago, there's a small, there was a small a medium-sized earthquake near the San Andreas, and the USGS actually sent out an emergency tsunami warning. But tsunamis actually don't occur on strike slip faults. Um, or at least large tsunamis. Strike slip meaning side to side movement. Um, they more occur at convergent margins. And so the water you would not expect a big tsunami, for example, if you're hanging out in Tomales Bay and a 8.0 went off. Maybe a small one, but I'd still rather be there than in a sub-basement garage or something.
I suppose though, if it shook large enough to knock some landform into the water, that could create a tsunami. So,
Yeah, yeah. I mean, and those types of tsunamis do happen. Like turbidity currents can actually cause tsunamis, but Tamales is shallow enough that I wouldn't be too worried about that
that's
personally.
true.
If you're in the open ocean, maybe I'd be a little more freaked out.
There you go, Larry. Paddle on.
Paddle on.
Okay. We're a little bit tight on time. We'll do a couple more questions. Maureen was asking about the water table in the Central Valley, lowering.
Oh yeah. Um, yeah, so there are these great photos out there. I don't know if you've seen where you can actually see we've been sucking so much water out of the Great Valley that it's actually been subsiding or moving down, and I think it's subsided over 100 feet at this point. So we've just been taking out all of the water from the Great Valley, and all that water was in the pore spaces in between soil and sediment, and that just causes it to shrink down further and further and further. How will that affect the coast in the future? Well, the big thing is um, it could have deleterious effects for like flooding because you're making bigger holes. You're making a bigger hole in the Great Valley, which means that it can accommodate bigger floods. And California actually has a quite a storied history of flooding. The last big mega flood was I think 1872 or the late 1800s. Um, and that I think that was responsible for like hundreds of mil like the entire Great Valley was inundated. You could kayak down the Great Valley. Um, I think like most of the animal population died because they all got drowned. They all drowned. So you get big flooding events, and we expect big flooding events to get more severe if you continue to subside the Great Valley. And also with climate change, big flooding events, big storm events will also become more severe. So maybe that's one side effect.
All right. So that Instagram video you shared was actually from Chris Manchester, who had down in Half Moon Bay kayaking, and he's actually one of the instructors in our skills clinic every year. Uh,
Wow.
but yeah, he's pretty commonly with the videos. So Cindy asked about the the sea tunnels and caves and how those form, like the ones in the video there. Is that just all water erosion, or is there something to do with the
Um,
rock types, or?
For Devil's Slide area, those sea tunnels are probably related to differential erosion. So, meaning that there are some areas of rock that are softer and some that are harder. So you can scoop out more material where there's softer rock. Um, so I would expect that the sea cave that is in Chris's video is related to that. And if you looked at the actual rock type there, I expect the Point San Pedro formation there to be very muddy. Mud is more easily erodible than sand. Um, so you can also get limestone sea caves, of course. So that's a different process where you actually are dissolving limestone, which is made of calcium carbonate, with
Hmm.
through slightly acidic rainwater, and that actually is causing dissolution. But those are not limestone. So yeah, that's some sort of structural cave caused by wave action on the coast.
Yeah, one of our favorite places to paddle is in the Mendocino area where there's just so many sea caves and tunnels and arches and stuff.
Oh
Uh,
yeah. Sounds
yeah,
amazing.
yeah. I'm just gonna do the one more question, a good wrap-up question. Can you recommend any books for people
Hmm.
that want to learn more?
I think the classic that every geologist says is the John McPhee books, which are, I would say, maybe read his book Basin and Range. It's a little dated at this point, so some of the terminology is a little out there, but I mean, geology is, we're all concerned about long timelines anyway, so it doesn't really matter too much. So I'd say John McPhee is great. Um, and I just read a book about Alexander von Humboldt that I really liked, who was not really a geologist, but an ecologist in the 19th century. I think it was called The Invention of Nature. And that also talked about Darwin a lot. And Darwin was a geologist, FYI, if you didn't know. Um, and I really liked that because it talked about like the intersection of geology, biology, ecology. It was a good read. So thanks for asking that.
All right. Well, just want to extend a thank you to Dr. Stephen Dobbs, and we appreciate you coming and giving a fascinating talk. Loved it, and I'm sure we could keep you here for a couple more hours with questions, but in the interest of time, and you probably need to get going. Uh,
Yeah. Well, thank you so much. It was really fun. Uh, uh, Thanks again for reaching out. Great opportunity. I'll be sure to recommend your organization and anyone getting interested in sea kayaking.
oh, great! And this video is recording. We're recording a video of this, so it'll eventually be up on YouTube, and we'll make you famous. So
Great. Okay. Looking forward to it.
I think you already are, though. So
All right. Well, talk to you guys later. See ya.
all right, thanks again. Bye bye.